Web assigned 7B number 6. Determine the amount of work that must be done on a 101 kilogram payload elevated to a height of 997 kilometers above the Earth's surface. Determine the amount of additional work that is required to put the payload in a circular orbit at this elevation. Part A asks us to determine the amount of work done to raise an object from Earth's surface to a point 997 kilometers above its surface. So to start off, back from the energy unit, we recall that work is equal to negative the change in potential energy, okay? So we know that work is equal to negative. Now, the change in potential energy is the final potential energy minus the initial potential energy. So that's what the change in anything really means. So then we know that work is equal to, and now plugging in what gravitational potential energy really is, Gmm over R. So the final potential energy is going to be Gmm over the final distance, while the initial potential energy is Gmm over the initial distance. But since Gmm are constants and the same in both terms, we can factor them out. This tells us that the work is equal to negative Gmm times the quantity of 1 over the final radius minus 1 over the initial radius. So now we get to plug in our known values. G is equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. We know that the final radius is going to be the radius of the Earth plus the extra 997 kilometers. So now the radius of the Earth is equal to 6.36 times 10 to the 6 meters. So now the final radius is going to be the radius of the Earth plus 997 kilometers, when you convert them to meters, is 997,000 meters. And then the initial radius is just going to be the radius of the Earth. Plugging this all into a calculator yields a work of 8.58 times 10 to the 8 joules. But the question wants the answer in megajoules. But 1 megajoule is equal to 1 times 10 to the 6th joules. So following this conversion, we know that 8.58 times 10 to the 8 joules is simply equal to 858 megajoules. And part B asks us the amount of work that needs to be done to send the object in the circular orbit at that elevation. So starting off with our general equation, we know that MA is equal to FG. But we know that in this case, the acceleration is going to be v squared over r because it's moving in a circle. And we know that the force of gravity is equal to Gm times big M all over r squared. So now the little mass cancels out. And then we're multiplying through the 1r. V squared is equal to G times big M over r. Now I get to take the square root of both sides, you get v by itself. V is equal to the square root of G times big M over r. And this big M here is the mass of the Earth, and this r here is going to be how far away the object is from the center of the Earth. So it's going to be the radius of the Earth plus the 997,000 meters. So now substituting in what we know. The velocity is equal to the square root of G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And the mass of the Earth is 5.97 times 10 to the 24 kilograms. And again, from before, we know the radius of the Earth is 6.36 times 10 to the 6 meters. Plugging this into your calculator yields a velocity of 7,360 meters per second. But that's not your answer. The problem is how much work is required to get an object from stationary to this velocity. So we know that work is the positive change in kinetic energy. And since we know that the initial kinetic energy is 0 because the object's stationary, the amount of work done is just equal to the final kinetic energy. And here we know the mass. This is not the mass of the Earth. It's the mass of the payload because it's orbiting around the Earth. And we know that the velocity is what we just calculated, of 7,360 meters per second. The mass of the payload is 101 kilograms. And the same velocity we just calculated right here. Plugging this all in your calculator yields a work of 2.74 times 10 to the 9th joules. When I originally did this problem, and when I was faced with the final versus initial radii, I just plugged in the 997,000 meters for the final radius and 0 for the initial radius, because I thought that it was just moving up. Then I realized that I had to take into account the actual radius of the Earth in my calculations. At first I didn't know how to calculate the velocity of the orbiting object, and I realized I had to go back to the basics of circular motion and substitute v squared over r in our force equation. And this problem shows my growth because it shows that I understand the topic of gravity and gravitational energy, that I also still remember that work is the negative change of potential energy, and I'm still able to use work and energy to solve problems. Thank you.